I recognize that many of us in this room are at all different stages in our careers. And so for myself, who's someone, maybe I think I'm starting to reach this mid-career point. And for me, as someone I've got about 15 years of experience now, mostly working in this geohazard risk management space, but I have never heard a lecture before in which there were so many kind of fundamental pieces of wisdom shared. She was just like throwing them at us. So I want to take a minute to, well, first of all, yeah, thank you so much for that lecture. But I do want to take a minute to say them again to you, to reinforce them, because I think that if Dr. Nalima's perspective, and then many of them directly align with the things that BGC has been sharing through some of our key messages and through some of the points I'm about to share in this lecture. So if you leave this workshop with these points, these are the kind of things that maybe you'll have some sense right now, depending again on where you are in your career, maybe you'll have some sense of, okay, someone told me that these are important, like I'll write them down, I'll keep them in mind. But I promise you that in 5 years or 10 years or 20 years, you will understand that this is it. Those big, thick textbooks are needed and important too. We need to have all that detailed technical knowledge, but if we don't have these kind of fundamental bits of wisdom, the textbooks are for nothing. Some of the things that I wrote down that really resonated with me were about, the code is just a guideline, it's not a law, especially for geotech. Design is judgment, it needs to be creative. Don't blindly take empirical equations or models for granted. Never, never. Please don't. Think about them. Use them appropriately. The need to look at site-specific conditions. Every project is different. That is written on the wall right there. And I'm going to have a few more slides on it in a couple minutes. The need to understand the process type and need to understand the physics behind a failure and not just kind of show up and take what you saw from one site and apply it elsewhere. You really need to understand, again, that site. Need to hear performance case studies from practitioners and to study failures. I am not, I'm a practitioner and a consultant, so I'm not a lecturer typically, but I do a guest lecture at the University of British Columbia every year. And every year I tell my captive audience of undergraduate and graduate students about the importance of case studies, and particularly in our field and the part in geohazard mitigation, where I design structures. One of the structures that Alex and I have worked on that is being constructed right now, the design event for this structure is about a 5,000-year rock avalanche. Turning into a debris flow, the Chikai barrier that we worked through those potential failure mode assessments. The design event there is a 5,000-year event. That is crazy. That's aside. We can talk about that separately. But that means that unless something goes very wrong and a very big mountain falls down, I will not get information about how my design has performed ever in my lifetime, in my career. So I will not, unlike a structural engineer or maybe other types of engineers, a mechanical engineer who designs an engine and then the engine is built and they get to see immediately how the engine performs. For us in geotechnical engineering and then particularly in this geohazard management space, it's very hard. I build a structure that never gets hit for 10 years or 20 years. So I don't have information about whether I'm doing a good job unless I look to other cases around the world, to what other practitioners are doing, and to the lessons learned from other events. So it's fundamental, absolutely needed for the work that we do, is to learn from case studies and how things are actually performing. Design needs to look beyond initial construction to long-term performance, operations, and maintenance. If you're coming to GeoMandu tomorrow, I'll do a pitch for my talk. It is called Maintenance Matters Most. So this is exactly in alignment. We can't forget that part. If we have a perfect design, but it's not maintained, as Alex was saying the other day, we failed. We didn't do a good job. So we need to consider all of that. The importance of multidisciplinary input. I'm going on to page 3 here. We're going strong. the need, every time as a designer, we're balancing something. That's another component. If you remember on the first day, Alex had a graphic with the kind of tripod of some of the things that we need to balance when we're doing the design, doing different designs. And that's something you'll always be navigating. One of my mentors talks about how on every project, every client will want to have a fast schedule, they'll want to have high quality, and they'll want to have low cost. And my mentor tells me you have to pick 2 of 3. You can only have 2 of 3 of schedule, quality, or cost. And so that's always a balance of which way are you going to lean and what thing is more important and what are you favoring. And then I also really appreciated the point about every project has a research component and the importance of research in our field. And that ties in as well to that need to stay up to date on case studies, on practice, and that's something that, Lauren is better able to speak to this. She is the research and development lead at BGC, and we are constantly sending students or sending employees back to go to grad school, connecting with academics, and working on different research projects to inform our work. It's been really helpful. And then the kind of final thing to sum that up is just that basic common sense and continuous learning are very important to the work that we do in order to be able to continue to take on the challenges that are coming at us in this really important and critical field right now. That is my kind of recap and acknowledgement. Again, thank you for your lecture. With that, I would like to resume where we left off yesterday with so if you remember, yesterday in the morning, I was up here talking about the town of Canmore and the Canmore case study, and that was the site where there was what was, for us in Canada, a large rainstorm event, a large and long rainstorm event that caused flooding and debris flows and debris flood issues in this mountain community. And we had talked about the decisions that were made for short-term mitigation, so what was done quickly on Cougar Creek, which was the area with the biggest problem. And then we had worked through that event tree risk calculation exercise so that you could build some confidence in completing quantitative risk assessment. So that's the equation on the board. Don't worry, we have finished the quantitative risk assessment portion of that, but I wanted to show you next up what the results were. So we worked through a more detailed version of that same exercise that you did, but with lots more branches on our event tree. But really the math is similar. There's nothing that takes what you did and makes it very different. All we're doing in this quantitative risk assessment is multiplication. No complicated math. But quantitative risk assessments were completed for all the major fans in the Canmore area. And this is the kind of information that those quantitative risk assessments gave us. So in Cougar Creek, which was that most densely developed fan, we've got the fan outlined here in yellow, and we've got the highway across, we've got the creek coming down, dense development, school, hospital, a lot here. We found that, one thing I should say is this particular municipality, this town, had adopted life loss risk tolerance criteria. So they had drawn a line and said, this is safe enough here in our community, this is not safe enough. And if there are people or things that are not safe enough, then we're gonna go try to find the money to fix that. So in this case, on Cougar Creek, we found there were 190 parcels with intolerable life loss risk, and that the annualized direct economic damages, so the annual every year potential for damages, was about $700,000 Canadian. So probably close to $1 million now if we were to look at it. On another site, this is a little bit of a smaller fan. So we've got a fan here. I'm sure it's a bit hard to see from the back, but generally you can see there's more green here on this fan than there is on the Cougar Creek fan. So this is Hart Creek. It's less densely developed. On this fan, there was only 2 parcels with intolerable life loss risk, and the annualized damages, direct economic damages, were only about $100,000. And then we had another site, this teeny little fan here. This is called Zed Creek. It actually didn't have a name when we started on it. It was such a little channel, but it had a debris flow. There's some houses right on the edge of this fan. None of those parcels had intolerable life loss risk, and the annualized direct economic damages were pretty low. So this was the information that we were equipped with coming out of, let me see if I put the slide in here. Oh, no, I didn't, Jack. So coming out of that prioritization step of our risk management framework. And we're starting to move into site-specific design. So deciding what to do with the resources that we have and thinking about, okay, given this information from the risk assessment, what types of risk reduction or risk management structures or methods are we going to consider on each of these sites? And so I would like to ask those questions to the group. Because we have 3 sites here, we're going to split the tables up a little bit. But I'd like you to do a little bit of brainstorming, maybe just for 5 minutes at your table about what risk reduction options would you suggest for each site generally, given your understanding of the risk. So we have a site with what we've defined as intolerable life loss risk and quite high annualized damages. And then as we move over here, we have a site where the life loss risk is tolerable, and the damages are low, but the community has still said, maybe we'll do something here if you can propose something that maybe doesn't cost as much. So those are the sites we're going to look at. I would like the first 3 tables at the front here to think about Cougar Creek, this site with the very high risk. This is the site where we had installed that short-term mitigation, the net, the 40-meter high, 40-meter wide, 6-meter high. That was only ever intended to last a few years, to just reduce the risk a little bit. There was always an understanding that something more was going to be done. So that was just an interim measure. So what ideas do you have for managing the risk here? The 2 tables at the back are going to think about Heart Creek, which is this kind of middle ground of risk, a little bit of intolerable life loss, a bit of direct economic damages, and then the 2 kind of front 2 on the left are going to think about this site that had lower damage potential. Any questions before yes?
So I wanted to parcel and
oh yeah.
And could you explain more about the intolerable life loss risk?
Yes. Okay, those are good questions. So parcel is just the word that we use in Canada to talk about. You have said this is one plot of land. Maybe that would be another word, a plot of land. Parcel would be another word. And so that'll be the plot or the parcel of land will have, maybe some will have a house, maybe some will have a business, some will have a business and a house, some will have a school. So it's just how many little bits of land within this bigger bit of land have high life loss risk. The piece about what is intolerable life loss risk is a deep hole that we could spend the rest of the day on. It's a very good question. So I think this is worth talking about. It's something that's very specific, maybe to the Canadian context and to the context of a few other places in the world. Here, maybe this will help a bit. I'm going to go back a few slides just to show you the graphs from the other day. Countries in the world and some regions and some towns in the world they've decided to adopt these life loss risk tolerance criteria. In Canada, we do not have any life loss risk. We don't have any codes for geohazard risk management in Canada nationally or at a provincial scale, to be honest. These are things that that there's no codes or guidelines for at this point. But in 2005, there was a fatal landslide that occurred in a very developed area near Vancouver, and it killed someone in their home overnight. And because of the resources in that particular community, it was a very rich community, they had the resources to say, this is unacceptable to us, and we're going to study everywhere within our community, and we're going to make sure that everybody can sleep safely in their homes. That was the decision to do that and to implement a life loss risk tolerance threshold, lots of words together, life loss risk tolerance threshold, was done just by that rich community. We have many other communities in Canada where that wouldn't be a choice that was possible. They don't have enough resources to make that decision. It's managed, I think, similar to Nepal, where it's the responsibility of the local government to deal with these things. And there's some support from higher levels of government, but ultimately it's the local government. And so Canmore, this area that we're talking about, is also a very rich part of Canada. That particular town has lots of people. The big city of Calgary is nearby, and for that reason, they had enough resources to also choose to do this. And what that means is that they are looking at all their risks using this quantitative risk assessment process and trying to manage risk for the people within their area. And the risk tolerance threshold that is commonly adopted is in Canada, and it's also used in Hong Kong, that's where it initiated, is 1 in 10,000 chance of fatality for an individual. So in a given year, your chance of dying for you in your house or going about your day from a landslide should be less than 1 in 10,000. Yeah, and that's about equivalent, and I recognize that Nepal is an entirely different context, but at least in Canada, the risk of dying from a motor vehicle accident is also about 1 in 10,000. So it's a comparable benchmark. You have about an equal chance of dying in a car crash as you do in a landslide. That's the target. Does that help? Any other questions on that one or about this example? I'm going to have to go over a couple slides to get back to where I was. Quickly, this isn't a big, complicated one. It's like, this is the problem you have, what kind of ideas would come to mind? All right. Looks like most groups have a few ideas. What are some ideas you have for?
We think that short-term reduction can be done by bank protection and executing the emergency rescue plan by building the multiple check barriers on upstream. For long term, we are thinking for bioengineering and rehabilitation of the infrastructure as well as.
Sorry, what was the last one?
Rehabilitation.
Debris flow from the upstream side.
Okay, yes. Yeah, good point. Trying to think about the best way to do that. Yeah. Okay, so
What questions asking about?
Okay.
We should propose the plan, isn't it?
I can't hear very well. Can you?
I think we should provide the plan, type of plan that question is asking for the plan, isn't it?
Okay.
So we have proposed that risk reduction options may be first is life safety based plans should be developed, and then after economic based plans should be proposed, and another is infrastructure safety based.
Can you hold the mic a bit closer? There we go.
Oh, sorry. Infrastructure safety based plans should be proposed. I think I may get wrong to the question.
Okay. No, I think that's good. So you're saying that we need to put plans in place as well that need to go with the mitigation structures that are developed. So rather than just the engineering measures, we need...
Somehow participants are telling that this way to prevent this kind of problem and that way to prevent this kind of problem. Instead of this question is asking for what kind of plan should we introduce to mitigate or reduce the effect of the debris, isn't it?
So you're asking what's the answer?
No. Did I get wrong or not? I just wanted to verify. is my concept is good or not?
Yes, it's good.
Yeah.
Yeah.
Thank you.
Thank you. Back to tables that we're thinking about hard.
Waste flow away from highly risk parcel. Only warning monitoring is the must, and a watershed management, that's all.
Excellent answers. That is exactly what happened at Hart Creek. So Hart Creek is a site where at the moment there's a highway near the top of the fan, but the houses are all further away from where the hazard comes out of the mountains. And so there's this area here that is not developed yet. So this is an opportunity to use land use planning and to say, let's not build a hospital there. Let's not put more houses at risk. And the other sending flows through the community. A retention structure and diversion structure was put in place just upstream of the highway so that very small flows still go through the community, but anything that is larger or unmanageable is sent this way and out to the river well away from the development. So that was excellent answer. Nice work. Curious to hear one of the groups that thought about Zed Creek, which is one of, we say Zed in Canada. Do you guys say Zed or Z? Yes. British.
Check dams made of locally available materials like wooden planks. And next is managing the surface runoff. Then maybe a plantation. Then also routine monitoring of the debris flow during, like before the monsoon begins. So we talked about those.
Perfect. Here, I'll switch slides here. The wooden planks. This is exactly what was done on this site. Here, the hazard was low enough and the elements at risk are far enough away that just simple wooden walls constructed with big timber and good posts, but maybe only a meter high. That it was enough to manage the risk. And these walls were actually in place before the 2013 event, and they performed very well. They were enough. And before seeing this on this site, I would not have thought of that. So I'm very impressed that this you were thought of this. Another option besides wooden walls here would be something just like an earth berm. A little earth berm or maybe a little GRS wall if you have limited space, geosynthetic reinforced soil, because that has a smaller footprint. But we're looking for something relatively low cost. So these are the concepts. I've kind of shared them already, what were actually built. On Cougar Creek, there was a very large retention structure built. The risk on this fan was so high and so expensive and so much potential for damage that the federal government, the government of Canada, pitched in with funding on how to manage this. The construction cost started out estimated at $40 million. The final cost was twice that, $80 million, and the structure was just finished a few weeks ago. It took a very long time to design and construct due to some of the issues that Dr. Nalima was mentioning and that we've kind of mentioned about design is not the last step. There's a lot of work to still do to make sure something is built properly. On Hart Creek, this is an example of the small retention and diversion structure. So this was a much lower cost structure that could be built much quicker. And this is a concrete wall with it was only 1 meter wide opening. And that 1 meter wide opening was sized to let the flows pass to the downstream community in an amount that was safe downstream. And any flows that are bigger get diverted around, as I showed you. And then here is a picture on Zed Creek of the walls, the wooden walls that were put in place. So excellent engineering design there. All right. I think we have a choice here given the time. I have some more slides about, and I could try to go through these as quickly as possible if you want this content, some of the things similar to the lessons that Dr. Nalima shared that I learned from 10 years working on these projects in Canmore. I've been involved since 2014, so pretty much exactly 10 years now, a bit more than that. The other option would be to just pause the lectures And Lauren has a group activity to do related to road design and geohazard risk management for roads. What is the group feeling? What are you feeling? What do we think? Are you done with lectures? Do you want a really quick lecture? Quick lecture? Okay. I can talk really quickly though, so be careful what you wish for. Wave wildly if you're like, no, just slow it down. Okay, let's do this. Okay, I need to start with this lesson because this is something, so the picture up in the top right is the key mentor for Lauren and I. The reason that we do this work is a man named Matthias Jakob. He unfortunately died 2 years ago, but the fundamental thing that he told me when I was young starting this work was that every creek or slope or river or hazard or site is different. And that was something, remember I was saying, like early in your career, you're like, yeah, old guy, like, you're okay, fine. Like, no, they're not. Like, eventually, if I do enough work, I'm going to come across 2 sites that are similar, and I'll just kind of do the same thing, and it'll be easier. No, just take this as a given. And the example I want to share here is that, so I work in Squamish. This is the big mountain in my backyard that could have a 5 million cubic meter rock avalanche off it that comes down to the Chikai Barrier. This is why we're building the Chikai Barrier, is to protect the community that Lauren and I live in. And this is the kind of mountains we have in Canada. Still much smaller than what you have here, but very big. But I had spent my career making decisions about what to do with our hazards in our mountains in Canada based on what they do in Hong Kong. And I thought, okay, Geotechnical Engineering Office, they have very good ideas. I'm going to do what they do and follow their lessons. And then in 2018, I had the opportunity to go to Hong Kong. And before my plane even touched down on the ground, we're flying in and I'm looking around and I go, oh, we have a problem. Hong Kong is different than Canada. Canada is different than Nepal. To Dr. Nalima's example, Japan and the rules they had is different from India. And we can't be directly taking things from any of these places. We can learn lessons, to my point about case studies and performance. We need to learn lessons from everywhere, and then we need to bring them back and think about our site-specific, key message over there, our site-specific context and things we know here. So thank you to my mentor, Matthias, for those words of wisdom. We'll skip this one, keep moving. I've shared about this one already. The past is the key to the future. We can use what's happened in the past to understand what might happen in the future. I mentioned yesterday the asterisk on that for climate change. Again, we're going fast, so I'll go through this quickly. Ask me about it at lunch if you want. Still start with the past. The past is the key to the future. But for climate change, we need to say, okay, this is what happened in the past. Maybe it's going to be 20% bigger. Maybe it's going to be 20% more frequent or 50% more frequent. But that decision should be done in a site-specific way as well, and a hazard-specific way. You need to think about your process type, because not every process type will change with climate change. Some might get more frequent, but smaller. And I think that we as practitioners and scientists need to understand and know that, because the people in government don't know that. They say, oh, climate change, everything will get bigger and worse. Sometimes that's not true. There are areas in the world where the hazards might be smaller. The Himalayas is not one of them. But it's not a blanket statement ever. You need to think that through. More methods, math, and models aren't always better, especially when there's limited resources. We fell into this trap in Canmore, actually. So those quantitative risk assessments that I shared that were useful for informing design, we did way too much science. We spent a lot of budget, a lot of money, and a lot of time doing a lot of very, very good science. We didn't need to do all that science to get good, useful answers. So we always need to be balancing and thinking about what is the purpose of what we're doing and how much of it is going to be useful. And sometimes if we're in academia or we're studying at a university, this is the thing to do and this is very useful and we as practitioners are going to use it and benefit from it. But if we're doing work to benefit a community or to inform decisions, do as little science as possible to an extent, and only do the science that's useful and well thought through. And we've run into this. This is an example of a town in Seton Portage. I mentioned earlier that not all communities in Canada have the same resources. Some are very rich and have lots of money. This is a community, an indigenous, mostly indigenous community. There are not many resources. We spent a lot of money doing a lot of science here, and then they didn't have any money left to fix the problem. I wish that we hadn't done all that science and all that modeling, and we had taken the little bit of money we had and put in a wooden wall. It would have made it a little better, made an earth berm, done a little thing. And so we need to think about what's the most kind of risk reduction we can do and balance that desire or that tendency that we might have as practitioners and scientists who have been trained on how to do a very nice run-out model. And we see, okay, there's this question. I know how to run-out model. Therefore, I will do a run-out model. Do you need to do the run-out model? Is it the best choice? Is that the best use of limited resources? Or are there other things you can do that are going to reduce the risk more and help more? Risk management should be proportionate to the risk. This is exactly the exercise we just went through that everybody nailed. Good job. Which is just to say, big risk, big structure, small risk, small structure. Keep those things in mind. We don't always see that done right. I've picked examples from Canmore where that was done right, but there are other sites where that hasn't been done right, and lots in Canada as well. Take small steps towards solving big problems. We had a big problem at Cougar Creek. The highway was closed. There are houses damaged. And there were a lot of people very kind of scared and confused about what to do about it. If we had gone right from this to the very big step, that would be a really big jump. And so we're going to split that up into the small steps. We're going to put something short-term in place that gives us some time to plan, to think, to do careful design of a larger structure that is going to ultimately provide the risk reduction that's needed. This also applies to sites where maybe you do have a big hazard, but you don't have the opportunity, and I think this is true in lots of Nepal maybe, to put, and in Canada, a very big structure in place. Sometimes what we do is manage these geohazard risks with something called a functional chain. So a chain, like a necklace, connected, all these pieces connected, and each one reduces the risk a little bit. The first step reduces the risk by 10%, and then 10% more, and 10% more. And this is just a very nice example of a site in Switzerland where that was done, where there was a few things put in place in a row that bring the risk down to a better level. Similarly, to the message a couple minutes ago about risk management being proportionate, decision-making effort should also be proportionate to the decision. So if you're deciding whether to buy an apple or an orange, you're not going to think about that too hard. If you're deciding whether to build a house or a big debris flow barrier, you need to think about that a lot. You need to get community engagement. You need to get government engagement, stakeholder, and everything else. So depending what you're doing, you're going to use different levels of decision-making. You'll have this slide deck, so you can take a look at this, but these are just some examples of what's a quick decision-making tool versus something at Cougar Creek that we used that was much more complex with lots of stakeholders involved. Another thing that I learned about at Canmore was just the group at the back that mentioned like using land use planning for Hart Creek, the opportunity to look for those chances where we have them, to use planning and policy to inform redevelopment. So in Cougar Creek, that could be used that the fan is fully developed, but we can still put policy in place that says, if you're going to build something new, build a better house, build it stronger, so a building code. Or, this is another site in Canmore where they are putting in new development, and we have an opportunity to say, so the red is hazard area, the yellow is where they want to put new developments, and we've been able to say, give the creek lots of space. Don't put new development right up to the creek. We learned our lesson at Cougar Creek, where everything was densely developed. We can do better than that going forward. And then we also, I'll skip that one, that takes your turn. So, a whole bunch of lessons learned. I hope that you remember some of those lessons, but really the consistent theme in all of these pieces is that risk management needs to be properly scoped. That very first step of the risk management framework, the defining the problem and the objectives, if you get those right, you're going to be in a way better place to get these other things right as you work through the design process. So, I put this up here. So, yeah, importance of that scope definition step for each of the subsequent steps. And actually how I've started to think about it is when I'm doing scope definition and thinking about problems and objectives and what I'm trying to do with the project, I actually am thinking about scope definition for each of the subsequent steps. So for step 2, for regional prioritization, I'm thinking about what are the study area boundaries, the hazards, the data availability, those things. I'm thinking about, for step 3, available budget, risk tolerance, technical capabilities, and then maintenance, budget for maintenance and capacity for maintenance. So that scope definition, you're thinking about all of the subsequent pieces. Oh, and that really comes down to, at the beginning of my talk today, when I first came up and I ran through the points that really resonated with me from the lecture that Dr. Nalima shared, if you walk away with nothing else from all the things that I have said, I hope that this is the kind of key message that you take away from the things that I have shared with you. Because if you go into your work really thinking about why am I doing this analysis? What is it going to be used for? Why am I drilling this drill hole? Why am I building a structure here? What is the problem? What is this for? What is the purpose? That will serve you very well, and it will serve your projects well, your clients well, your country well. The big problems that we're trying to face will be helped by remembering the purpose and thinking about the purpose of what you're doing. Thank you. With that, I'm going to pass it to Lauren for some more interactive stuff.